Hello. Okay, today we will be talking about the differential amplifier. That is a bipolar junction transistor amplifier that produce output that are a function of the difference between two input voltage. Okay, now you're looking into here. You can see you can get one transistor Q1 and another one Q2 transistor. Okay, so if they if you're looking into the circuitry connected well, what happened? What amplified for Q1? Can you tell me? Q1 connect either will be common emitter, common collector, or common base. Okay, so I can tell you, okay, Q1, Q2. And Q2 will be the amplifier, common emitter, amplifier. Okay, if a C amplifier, then input and output will be 180 degrees our phase. Input and output 180 degrees. Our phase. Okay, that's what you have to hear. And now this is a circle. Okay, and this will be a symbol. Okay, okay, this will be a symbol. Now you see, assume both transistors are identical. RC1, RC2, okay, will be the same. So I1 and I2, the same, will be the same. And they will be equal. Let's see, IC1 equal IC2 equal IRE divide by 2. Okay? Where IRE equal VE minus VE divide RE. That's what we get IRE. Okay? And VC1 and VC2. Okay? VC1 or VC2 equal VCC minus IC1 times RC1. Okay? Same thing for I equal VE equal VB minus 0.7. That happened to the fourth transition. Okay, now we'll see. First thing, they connect Q1 back to route, Q2 back to route. Both input router, and they connect the meter, okay, to measure the voltage and collector, same thing. And look like both voltage will be the same. Okay? And now, for this configuration, sideway connect to VB1. Okay? That means they connect the signal into VB1, a sideway. Okay? So Q1 will be the amplifier. Input, output Q1 is inverted. Okay? So they connect the input sideway into the base of Q1. Okay? Then Q1 will be the amplifier. And if you're looking into the input, you can see this is input. And the output here, they will be opposite. Okay? Now, they connect the Q2, the base, to the route. Okay? See what happened. You can get a sideway and at the collector here. Also, you get a sideway. And this sideway goes into F meter up to 2. Okay? So go to the F meter and the output from the collector. Okay? So for this configuration, VB2 is right. Okay? Q2 will be CB amplifier. Okay, it's CBM refinement. Input, output Q2 will be in phase. Okay, so you can see if you get the input sideways here, and this also sideways, and the output on this one will be sideways. The thing is, the Q2 will be common base amplifier. Okay, so what they're telling you here, bias voltage on input one with input to grounding. Okay, so basically, in this case, Q1 will be common emitter. So that's why you get input and you get output. Input output will be 180 degree out of phase. So you get a sideways at the base Q1, and you can get at the emitter, you get a sideways. And this sideways go into emitter of Q2, and Q2 will be common base of the amplifier. So the output will be same phase with the input. Okay, that is you need to recognize. Okay, now for this configuration, they do opposite. That means they apply sideways, okay, into the base of Q2. They're telling you now Q2 will be common emitter. Okay, so the output here will be opposite, okay, with the input. In and out, 180 degrees different. Okay, and right here, you also get sideways. And this side, you get a sideways. So now Q1 will be common base. Okay, so the output in phase. Okay, with the input. Okay, they just try to do different from the first one. Apply input to Q2. Okay, and input of Q1 will be rounded. And Q2 now will be common emitter. Output input will be 180 degrees out phase. That's what you can see. Input output 180 degrees out phase. And the Q1, even they grounded the base. Okay, and now they're working like common base. They're telling you that input and output will be in phase. Okay, Okay, they did picture the just draw, make it more clear. Okay, so when they apply input to Q1 and input Q2 rounded, output of Q1 will be the amplifier. They will be opposite with the input signal. And the Q2 now will be, you see the signal coming to the meter. Okay, and Q2 will be a common base. And that input output will be in phase. Okay. Now they just try to opposite. Okay. Input sideways apply to Q2. And Q2 will become an F meter. Okay. So output here opposite to the input. And also Q1 now will be common base. Okay. Input, output, in phase. That's what they want you to know up to this point. Okay, this is mode of signal operation, single ended input. Okay, when a different amplifier operates in this mode, one input is right and the signal is applied only to other input. So you know that is a differential amplifier. They get two input, two output. However, in this case, they apply only signal to one input and another one will be routed. Okay? Either to apply to pin 1 or apply to pin 2, doesn't matter. Okay? And look into the output. Okay? Output 1. They will be opposite to the input signal. Output 2 will be in phase with the input signal. Okay? Now, differential input to opposite polarity out of phase signal applied to the input. You say, you get an amplifier V in 1 applied to input 1, V in 2 applied to input 2. Remember, both input, they have to be opposite. This going up, this going down. Okay? And the output 1, you get this signal. Okay? They will be opposite to the input 1. And output 2, you get this signal. And this signal will be opposite to V in 2. Okay? Common mode input. Both input are the same phase. same frequency and same amplitude, okay, are applied to the two input. The output are superimposed and they are cancelled, resulting in a zero output voltage. Okay, common mode input output are superimposed and they are cancelled. Okay, if you apply the same phase for both, this action equals common mode rejection. Okay, if you apply two inputs at the same phase, they will be cancelled at the end. Common mode rejection. Okay, means that this unwanted signal, noise signal, will not appear on the output, the desired signal. Common mode signal. That means the noise generally are the result of the pick-up of radiated energy on the input line from adjacent line. Okay? So remember, up to input signal, if they will be the same phase and the output they cancel out, they consider that to be the noise. Common mode rejection ratio, CMRR. The measure of an amplified ability to reject common mode signal is parameter called common mode rejection ratio, CMRR. CMRR basically equals AVD divide ACM. AV, the gain of differential amplifier, where AVD is a differential voltage gain and ACM is a common mode gain. The higher the CMRR, that will be better. The CMRR often expressed in decibel dB. Okay, this is the formula we need in order to calculate the CMRR in dB. Okay, example. A differential amplifier has a different voltage gain every day, 2000, and common mode gain ACM 0.2. Determine CMRR and express it in decibel. You know CMRR equal AVD divide ACM 2000 divide 0.2. You get 10,000. And now, if you want in decibel, apply formula 20 log of 10,000 equal 80 dB. Okay, and you can try on the V part. Okay, for the differential amplifier circuit slope, single-ended output. Normally, to see the output will be out1, out2. However, now they're using only one out, single-outed. Okay, given AVD 2500 and CMRR 30,000. V in 1 500 microvolt. Okay, this is a V. Let's see, V in 1 500 microvolt. AVD voltage differential 2500 and common mode rejection 30,000. Okay, now at the same time, a 1 volt 60 hertz common mode interference signal appear on both input, and now you get at a both input to signal that will be 1 volt. Okay, 60 hertz. Consider to be the noise effect to both input of the amplifier. A. Determine the common mode gain ACM. Okay, you know CMRR equal AVD divide ACM. So that's telling you ACM equal AVD divide CMRR. 2500 divide 30,000. Okay, equal 0.083. Extract CMRR in dB. You know how to do that. Turn it out 30,000. You get 89.5 decibels. Okay, VE different equal V in 1 minus V in 2. V in 1 is 500 here. V in 2, nothing. We don't have an input 2, 0. So you get 500 microvolt. V out equal AVD. Okay, time V in different 2500 time 500 microvolt. Microvolt IMF. So that gives you 1.25 via MF. And now you can see, do same thing like the last one. However, a different way. They apply V in 1 and they apply V in 2. One thing, we have to pay attention. V in 1, V in 2 must be opposite. Okay? Also, in the V in 1, you can get a 1.60 hertz. Look like a noise. Same thing for input 2. Okay? So, for the differential amplified circuit show single-ended output AVD 2500 and common mode rejection 30,000. V in 1 equal V in 2, 500 microvolt VINF. At the same time, 1 volt 50 hertz common mode interference signal appear on both input signals. They want to know via RMS output. Now, V in different equal V in 1 minus V in 2. That means 500 microvolt minus to minus 500. The thing that they opposite. That current 1 millivolt RMS. Therefore, V out equal AVD times V in different 2500 times 1 millivolt RMS. You get 2.5 volt RMS. Next one, okay, ACM equal VRCM divide V in DM. Okay, VRCM equal ACM times V in DM. Okay, V in VCM equal 0.083 times 1 volt. Let's see, VE, that will be 1 volt. Okay, so they given you 83 millivolt. Okay, so basically, this very simple about the differential amplifier. Okay, so okay, the lecture will be stopped at this time. Okay, thank you. Bye bye.